Okay, we're looking at now an equation that has an oblique asymptote. How do you recognize an oblique asymptote from a horizontal asymptote? Well, if the numerator of the function, the degree of that, is 1 higher than the degree of the denominator, then what you're guaranteed to have is a linear oblique asymptote, a slant asymptote if you wish. Now, how do we graph a function such as this? What are the things that are important? First off, obviously, a restriction is important. So within the domain, we can state the restriction. So the domain helps us put a place for our restrictions, because in our graph, the domain is restricted by any sort of vertical asymptote or hole that may exist. In this case, we don't have a hole because we can't factor the numerator so that we can eliminate the x minus 1. Next part that's important in a graph are the X and Y intercepts. Those are crucial enough that you should automatically want to look for them. The Y-intercept is easy because you substitute x for 0, so we plug in 0 here, and we end up with a value of 2 for the y value. So it's 0, 2, where the graph crosses the y-axis. Next, we're looking at the x-intercepts. Now the x-intercepts are at plus or minus the square root of 2 over 3, 0. If you type plus or minus root 2 over 3 in your calculator, you're going to end up with plus or minus root 6 over 3. And in grade 11, you learned that this is not an acceptable answer. This is because the denominator is rationalized. The denominator is not allowed to have a sign, a decimal, or a root sign. So a negative sign, a decimal, or a root sign. It is not allowed. So what happened was that, all right, and then last but not least, root 6. So these are the same values. These are all going to be the same. What you have to do is approximate a decimal for this answer, because that decimal is the one that we're going to graph, folks. Okay? So it's going to be plus or minus 0.8, 0. So that's where our x-intercepts are going to be. Okay, now, how do you get this plus or minus root 2 over 3? This is going to be the question that a lot of you probably had. Up until now, you're probably confused how all these get there. So let's go back a couple of steps and find out how we got the first one. Well, we set it equal to 0. Then we moved everything to one side. So we took 3x squared is equal to 2. Then you divide it by 3. X squared is equal to 2 over 3. Now, you have to think, what number squared gives you 2 over 3? Well, yeah, you all know to take the square root, but you forget that it could be positive or negative that could be squared to give you 2 over 3. So our final answer has to have two possible values. Positive, whoops, sorry about that. Let's go back a step. Positive or negative root 2 over 3. Okay. This positive or negative root 2 over 3 is not allowed to be the final answer. Even though we started it off like that, you automatically saw that I gave you this. How did we get this step? Well, that is, you take positive or plus or minus root of 2 over 3 is the equivalent of saying root 2 over root 3. And notice that there's a root on the bottom. This root is not allowed. Therefore, we multiply by a magic number 1. I'm going to multiply both top and bottom by the magic 1 called root 3 over root 3. What that allows us to do is eliminate the root on the bottom so that you get root 3 times root 3 is just 3. That's this here. Oops, 1 second, that's this here. And root 2 times root 3 is just root 6. So that's how the calculator got that answer. Finally, to get this answer, hopefully all of you know, is you just convert it to a decimal. So it's root 6 divided by 3 in the calculator, and you get 0.8. Or you could have used this to get this. The goal is, this is the answer that you use to find it on the graph, but this is the correct answer for your final statement because this is the exact value. So this one here, folks, is the most important one of all. All right. Next. We're going to look at now how to get the oblique asymptote. You know that there's a vertical asymptote because in the restrictions, in the denominator, we have x minus 1. It couldn't be eliminated, so what we had to do was, we know then that becomes our vertical asymptote. We know that there must be an oblique asymptote, so we have to find that oblique asymptote by doing long division. So that's what's going to happen here. The long division of it is as follows. And this is what you end up getting, knowing how to do long division. The remainder, one day we'll figure out what it has to do with. At this point in time, we don't worry about it. This is the number that we're going to focus on, 3x plus 3. Y equals 3x plus 3 is going to be the equation of the line that is known as the oblique asymptote, the slant asymptote. And there we go. Here it is. So we've listed the asymptotes, we've listed the intercepts, we've listed the restrictions, also within the domain. And now we're going to look at the graph. But before we do that, we need to find the positive and negative intervals. Positive and negative intervals are the same as you did in the last unit. It's basically what we're trying to find out is when does the graph go in the positive area, so above the x-axis, and when does the graph go below the x-axis. So all the intervals are stated based on the vertical asymptote and all the x-intercepts, because that would be the only time that the graph could possibly cross. So within the interval, you can use, now, negative 0.8. Technically, negative 0.8 is not the exact value. You know that it's this number because we need to be able to graph it. But really, within the interval, if you were to state it, you actually have to get rid of that 0.8, folks. Yes, sorry about that. And actually use negative root 6 over 3. But knowing that will be 0.8, we can choose a test point that is appropriate. Then the next interval is going to be, now you're probably thinking, okay, negative 0.8 and 0.8, which technically could be correct, but it's not the exact intervals. So if you were to state the exact intervals, that would not be acceptable. You would have to go negative root 6 over 3 to positive root 6 over 3. But keep in mind, you know the decimal, so that will help us find the value that we're looking, that we can use. The next one is obviously going to go from 0.8, which is root 6 over 3, up to 1. Then we're going to go from 1 to infinity. Sorry. So we need now to determine test points. In the first one, the test point is going to be negative 1. The second one, negative 10. Sorry, negative 10. It could have been negative 1, negative 10, negative 100, any value that you want here to calculate from negative infinity up to negative 0.8. Next one, we want from negative 0.8 to 0.8. Hopefully you're thinking the same thing I am. 0. Next, from 0.8 to 1. Well, we're going to have to pick 0.9. Next, from 1 to infinity. So from 1 to infinity, we're going to pick 10. Put in values, these values, test these points into the equation here. What do we get? Well, the top number, if I plug in negative 10 up here, I'll get a positive value. Plug in negative 10 on the bottom, I'm going to get a negative value. My final result will be less than 0. Next, plug in 0 for the numerator, you get negative. On the bottom, you get a negative. And the function is now going to be greater than 0, so above the x-axis. Next one, we'll plug in 0.9. We get a negative on the bottom and a negative on the top. So positive on the top. So our function will now be below the x-axis. And finally, 1 to infinity, we plug in 10. The numerator is going to be positive, denominator is going to be positive, so the final result will be greater than 0. Alright, we're going to stop the video here and move on to the graph in the next video. See you on the other side.